One is up to the standard error, whatever we have done up to standard error. So after standard error, we started the hypothesis testing part. So hypothesis testing will not be asked. Up to standard error, I'll be asking in CIA 1. So we started the hypothesis testing part. Just a quick recap. We are talking about a simple regression with one y and one x variable, y being the dependent variable and x is the explanatory variable. And we we went forward to calculate the estimators beta 1 hat and beta 2 hat, and then their standard errors beta 1 hat and beta 2 hat. And now we are testing hypothesis about whether the slope coefficient in the population is zero or not. So in other words, we are trying to test the hypothesis that whether x and y are related at all. If the null hypothesis is rejected, we conclude that there is a significant relationship between x and y in the sense that x affects y. And if we are not able to reject the null hypothesis, we will conclude that x does not affect y and that uh, there is no relationship between x and y. So we discussed about what is a null and alternate hypothesis. Uh, we discussed that when are we going to, what is the rule for rejecting or not rejecting the null hypothesis? We discussed that it is the p-value which is important, and if p-value is less than or equal to 0.05, we reject the null hypothesis. Then we discussed that what is actually the p-value, and we used uh, this graphical uh, presentation to understand that where is this p-value located in terms of probability on the graph. I used green color for the p-value. So the area under the curve, which is in the tails, is the p-value. For the t-statistic, which is the dividing line between blue and green. So because in regression we have a two-tailed test, we are looking for both the tails and there are green areas in both the tails. We add them up together, do both the areas, and the sum of those areas under the tail is the p-value.
Excuse me, sir.
Yeah,
Could you let other people in?
all right.
Thank you, sir.
So we discussed last time that how to uh, readjust the scale, beta 2 scale onto the t scale, and we found that there is a one-to-one correspondence between the beta 2 scale and the t scale. We converted the sample statistic into onto the t scale using standard error. There's a simple formula that if we take the ratio of the sample statistic beta 2 hat in this case divided by its standard error gives us a t value of 2, suppose, then we can see the correspondence between beta 2 hat, which was 2000, and t, which is 2. So in effect, we are trying to see that how much area is there in the tails to the right of minus, to the right of 2 and to the left of minus 2. And that would be the p-value of the t statistic. If this p-value is less than or equal to alpha, where alpha is level of significance, and suppose we assume it to be 5%. So if p-value is less than 5%, we reject the null hypothesis. Uh, we also discussed that generally we use 5%, 1%, and 10% alpha levels and not other levels. But it is always possible to use any level which you wish to take. Uh, the higher the alpha, the less the accuracy or precision with which you are making a statement. So if your alpha is 1%, that means you should be, and if you are able to reject the null at 1%, that means you are very sure in this case that what you suggested, that means you said that beta 2 is not equal to 0, you are saying it with great confidence. When you are taking alpha to be a big number, for example 10% or 20%, in that case, even though you are rejecting the null, you might not be very assured of your result. So setting alpha to low levels, for example like 1% or 5%, is uh, having more confidence in your results, and setting alpha to big numbers like 10% or 20% or 30% means that you have less confidence in whatever result you got. So it's up to you whether you want to work at a low alpha or a high alpha. And if you're working at somewhere in the middle, like 5%, which is generally the case, it's not very low, that up to 1%, and it is not high up to 10-15%. So it's in the middle. So generally people work at 5% alpha. So in this case, I will be using 5% to be my alpha, and you can take it for granted for any further analysis. So I'll be referring to 5%, and it should be clear to you that I have decided to use 5%. It's not that it's only 5% that we can take. All right, so uh, now that we have an understanding of the meaning of these terminologies, we can use one example of ours to see what happened in that case. So if you remember, we were using some x and y values and one example. In that case, let us check whether there is any relationship between x and y. So I'm going to switch to Excel. Before that, if you have any question from any of these things, if you want me to say more about any of these things, if you want me to repeat any of these things, if you did not understand any concept, please let me know. So I'm coming back to the example that we took, and we made certain calculations. All the things which we have calculated, I turned them to yellow in the regression output given by Excel. We have a y variable and x variable, and we want to see the results of our regression of y on x. So here are some calculations that we made. Uh, Today we are going to see the hypothesis testing part here. I'm going to start with the t statistic here. So we have a t statistic, and it is very simple to calculate t statistic using the formula that we discussed. So I'm writing t stat, and I'm writing beta 1 hat, and then I'll be calculating t stat of beta 2 hat. So the formulas are simple. Uh, I'll just divide the value of the statistic with its standard error. So let me put the standard error, or okay, let me take the standard error from the table itself. So, or let me put it here first. So I asked you to calculate the standard error of beta 1 hat yourself, which you would have done. So here I am putting the value as it is. Now for t statistic of the beta 1, I'll divide beta 1 hat, which is 4.5, by its standard error, which is 0.6, 2.02, and I got 2.22. And then similarly, I'm going to divide beta 2 hat, which is 0.5, which we calculated before, by its standard error, which is 0.64549722. We got it to be minus 0.77. You can verify that these two numbers, 2.22 and minus 0.77, are here in the regression output. So we have done, we have calculated the t statistic also. Now coming to the,
Excuse me, sir.
yeah.
So from the starting, if you're sharing your screen, sir, it is not visible to me and Ashish. We are just seeing a blank screen. Like I have tried to join from my phone and laptop as well, but it is just showing a blank screen to us, like the black screen.
Okay. So
So
is it
from
the
the
case?
starting, when the like I was thinking that it is only for me, so I was not seeing anything. But Ashish also has having the same problem.
All right. So is it the problem with others also? Please raise your hands. Okay, there are many people. Five, five people who are not able to see the screen. All right. So I'm going to share it again. Let's see if it is visible to you.
So now it is visible. Thank you, sir.
All right. So so these are the two numbers that we can calculate just by dividing the betas with their respective standard errors. Now coming to the p-value, p-value is the area under the tails. For example, if we take this t statistic here, so I'm drawing it here. So if 2.22 is the statistic, so it's a two-tailed test. So we have a 2.22 and we have a minus 2.22, right? And the green area is the p-value. So we want to see how much is it, right? How much is it? So that's a measure of p-value. If it happens to be less than 0.05, we will reject the null. And we can see the t table for this, but I'll show you the t table. But before that, let me show you how to do it in Excel. All right, in Excel, uh, I'm writing p-value, and this is for beta 1 and p-value for beta 2. In Excel, we can do it by writing a formula. Of course, you will not have access to Excel in the exam. Then you have to see the T table for that. So for beta 1 hat, which has a T statistic of 2.222, we can simply write TDIST, TDIST, and then we can put the value of the T statistic for beta 1 hat, which is 2.22. That's the first argument. Then comma, you can write degrees of freedom. Degrees of freedom is n minus k. So there are, the sample size is 5, and parameters to be estimated is 2, and 5 minus 2 is 3. So I'll write a 3 here. So that's the degrees of freedom. So we need degrees of freedom to calculate the p-value. Then how many tails you're working with? So I'm writing 2 here because I'm working with 2 tails. So we have a 2-tail test. Then I'll press enter, and it will give me the p-value of beta 1. Similarly, I'll do the same exercise for beta 2. I'm writing the formula again. I'll write TDIST, which says T distribution, and then I'll write the T value for beta 2 hat, which is minus 0.77. And then I'll write degrees of freedom. And then I'll write 2 tails, and then I'll press enter. It says error because my T value is negative. So to make it positive, I'll put a minus sign from my side. Now it is showing 0.49, 0.112 and 0.495 are the two numbers in the Excel output also. So I'm going to make them yellow. Now calculating the confidence intervals. uh, Before coming to the confidence intervals, I will leave this for future. I'll talk about it later, maybe today or tomorrow. Before that, I want to come to the F statistic part. So you have an ANOVA table, and in ANOVA table, we have sum of squares, regression, residual, and total, which we have already calculated. Now there is another column called MS. MS means mean sum of squares, right? So mean sum of squares is sort of taking the average, and if this one has to be divided by its degrees of freedom to write what is the mean sum of squares. So this number that we got is simply the sum of squares divided by its degrees of freedom for the ESS, and we got a 1. And similarly, the sum of squares RSS, which is 5, divided by the degrees of freedom of the RSS, which is 3. And when we do it, we get 1.66. So this 1 and 1.66 is just the mean sum of squares of ESS and RSS. So I'll make it yellow. Now, F statistic is
Excuse me, sir.
yeah.
Sir, could you please repeat this?
This we have already calculated the degrees of freedom and sum of squares. Now we are calculating mean sum of squares. So we have 3 sum of squares: the ESS, the RSS, and the TSS. Right? So we have degrees of freedom for the ESS, RSS, and TSS to be 1, 3, and 4. And we have sum of squares due to regression, which is ESS, due to residuals, which is RSS, and total, which is 6, which is here in SS column. Now we are trying to calculate the mean sum of squares. So we will be dividing the sum of squares by their degrees of freedom. So if we divide 1 by 1, we get a 1. And when we divide 5 by 3, we get 1.66. So we have divided the sum of squares by their respective degrees of freedom. and we got mean sum of squares. Now we can use these mean sum of squares because if you remember, we talked about r squared, and r squared was uh, ESS divided by TSS, right? Now, if we take that ratio, not ESS divided by TSS, but if we take ESS divided by RSS, right? So you can understand the meaning from the ratio, that what percentage of total variation was explained by the regression is R squared, and what percentage of residual or RSS is the uh, ESS, right? But we are not taking the sum of squares, but we are taking the mean sum of squares. That's the only difference between F statistic and R squared. So let me write a few one or two equations here that would clarify what we are doing. So I'm writing it here. Number 5, F statistic is equal to mean ESS divided by mean RSS, right? So what are we getting by taking this ratio? Basically, we are trying to see, compare the ESS with the RSS, right? So remember, ESS is what is explained by regression. What part of variation in Y has been explained by regression is the ESS. And what part of the variation in Y has not been explained by the regression, or what remains to be explained by regression, is the RSS, residual sum of squares, right? So we are trying to see that how big is the explained part as compared to the unexplained part, right? And we are talking in terms of mean just for the sake of statistic. The F statistic is constructed using means, right? But we can think of intuitively as measuring something, with measuring how much is the explained part as compared to the unexplained part, right? So if we take this ratio, we get the F statistic, and this is simply calculated by taking this ratio. So I'm writing it here. I will divide the mean ESS, which is 1, by the mean RSS, which is 1.66666667. And when we do it, it turns out to be zero point 0.6. Now, this zero point 0.6 is, you can think of it as being 60%, right? So if you make a comparison of the mean ESS and mean RSS, the explained part and the unexplained part, the explained part is just 60% of the unexplained part. Or if you want me to say something not in percentage but in these decimals, so I'll say that if RSS is 1, then relatively the mean ESS would be zero point 0.6. Of course, zero point 0.6 is 60% of 1. So that's two ways of saying the same thing. So this is your F statistic. I'll turn it yellow again. So we have calculated this. Now this thing is nothing but the p-value of the F statistic. So as we have a t distribution, we have a F distribution also. And and we have a p-value of the F distribution also. So if suppose we have a F distribution, and then there is some value here, which is 0.6, then we can find how much area is there in the tail. So that is going to be the p-value of the f statistic, right? So any distribution which you are drawing can have a p-value. P-value is the probability, which is nothing but the area under the curve with respect to a certain value. So what is the p-value of the f statistic, which is zero point 0.6, right? Now, f statistic has numerator and a denominator, right? So we have ESS in the numerator and we have RSS in the denominator. Of course, mean ESS and mean RSS. So we have the degrees of freedom for the ESS is 1 and the degrees of freedom for the RSS is 3. So numerator degrees of freedom is 1 and denominator degrees of freedom is 3. So we have to use these two numbers in the F table to calculate the p-value of the F statistic. But we will see the table later. Right now, I'll be using Excel to calculate this p-value. So p-value of the F statistic. So you can use FDIST and you can put the F statistic as the first argument, which is 0.6. So I'm writing it manually, 0.6. Then it asks for degrees of freedom in the numerator. So there is 1 degree of freedom in the numerator, and how many degrees of freedom are there in the denominator will be the third argument, which is 3. So given this information, we will get the p-value of the F statistic, which is 0.4950. And we will use the table, and I'll show you how to use it later. So I'll turn this also yellow. So I have to explain you this whole concept of F statistic and F distribution. Now I just explained you how to calculate these things. Now I will tell you what is the meaning of these things in a more detailed way. So that's the calculation part. I'm switching back to PowerPoint. If you have any question in calculation part, please ask.
Understood, sir.
All right, what about others?
Understood, sir.
All right. So let me switch back to PowerPoint to explain the reason why we of the ANOVA table in the regression output, and why do we do an F test, and what is the difference between F test and T test. So we have a few questions to answer here. I will be talking in these terms. Let me write so that I don't forget. So I'll be talking about the F distribution. I'll be talking about why ANOVA table. I'll be talking about difference between F test and T test. So let us start with the F distribution. Basically, F distribution is skewed to the right. It looks like this, right? And we are starting from 0 in the F distributions, so we don't have negative values in the F distribution. So F statistic is always positive, and there is one value. All the values have on the F on the x-axis would divide the curve into two parts. For example, if I have this F value of 0.6, would divide the whole distribution into two parts. One is going to be the area to the right of the value, and then another is going to be area to the left of the value. The area to the right of the value is nothing but the p-value. Of course, area to the left is also a probability value, but when we refer to the p-value of the F statistic, what we mean by this is this green area, right? Area in the right tail. That's the p-value of the F statistic. So if you have any value for the F statistic, it is going to be greater than 0. And if you locate it on the x-axis, it will divide the F distribution into two parts. Of course, the entire area under the curve is always 1, whether it's a t distribution, F distribution, chi-square, or any other distribution, beta distribution, Cauchy, binomial, Poisson. All of them have area equal to 1 under the curve. The total area is 1, right? So these dividing lines or the values of any statistic divide the whole area into two parts, right? One is the area under the tails, and another is area in the center or area in the body, right? So that is the case here also. So we refer to the p-value of the F statistic to be the area in the right tail, which which gives a probability value, and again the rule remains the same. It says that if p-value is less than or equal to 5%, we reject the null. So up to this point, everything is same as we are doing with t distribution or t statistic conceptually. Now, the null hypothesis in case of a F distribution is all slopes are 0. All slopes are 0, right? And the alternate hypothesis is at least one of the slopes is non-zero, right? So you can put this null and alternate hypothesis in different into different statements. I can also say, when I'm saying all slopes are 0, what I mean to say is that none of the x's affect y. And the alternate hypothesis, when I'm saying at least one of the slopes is non-zero, I'm saying that at least one of the x's affect y. So here we are talking about y equals beta 1 plus beta 2 x plus u. So there is one y and one x. We call it simple regression. But we will be dealing in future with multiple regression, which looks like this. We have one y and many x's. This is called multiple regression. So in this case, when we will be doing multiple regression, F, F test will be important. In simple regression, F test is not important because we have only one X. If you see the null hypothesis, it talks about all slopes are zero, but there is one slope, which is beta 2, right? So there is only one slope. One slope only. But here we have many slopes. Right? Beta 2, beta 3, beta 4, there are three slopes in this example. So in multiple regression, we have at least two slopes or more than two slopes. So if we want to test whether all the x's affect y or not, or we want to test whether all slopes are zero or not, we use the F test, right? So F test is used for all slopes together being zero or not, and t-test is used to check individual slopes one by one, right? So the question that we are asking in f-test is different from the question that we are asking in the t-test. In the t-test, we are asking a question whether beta 2 is zero or not, and we will get an answer. We will ask another question whether beta 3 is 0 or not, and we will get one answer. If it turns out that beta 2 is 0, then we will say x2 does not affect y, and beta 3 is not 0, we will say x3 affects y. But in the F test, we do a combined test for all slopes. So if we are trying to ask a question whether the regression is meaningless or is it meaningful, if at least one of the slopes is non-zero, our regression is meaningful. If all the slopes are zero, there is no point running a regression. So F-test is a combined test for checking whether all the x's are not affecting y, or there is at least one x which is affecting y, right? So that's the difference between F-test and t-test. And the question why there is ANOVA table. ANOVA means analysis of variance. So when we are calculating the variance, three variances, which are ESS, RSS, and TSS, and we are trying to use them calculating mean ESS and mean RSS, and then using these two to calculate the F ratio, which is the mean ESS divided by mean RSS. Basically, we are doing some sort of analysis on the variance because this is the variation in explained part. This is the variation, how much of variation is there which is not explained. So it's variation, it's variance, right? Variance in residuals. And this is total variation which is there, the TSS. So ESS, RSS, and TSS are basically variances of the explained part, unexplained part, and the total variation. So this is nothing but analyzing the variance in the explained part, the unexplained part, and the total part, which is there to be explained. So in that sense, we have an ANOVA table which analyzes the variance. So if you have any question from here, you can ask regarding the F test.
Understood, sir.
All right. So what about others? Everyone got it?
Excuse me, sir.
Yeah.
Sir, could you please tell that the area to the left of the value is called?
The blue area.
Yes, sir.
The blue area is the probability of x, or here we have a f statistic. So let me write a f here. Probability of f being less than 0.6, and area to the right of zero point 0.6, including zero point 0.6, is telling us the probability of f value being greater than 0.6, right? So we call this to be the p value. It is popularly known as p value. It doesn't mean that the blue area is not a p value. That is also a probability value. But when we refer to p value of the f statistic, we are concerned with the area to the right, the green area, by convention.
All right, sir.
So can you please tell what is written is variation in expand and variation in what is written for this ESS and RSS? What you have written?
I've written variation in explained part of uh, of y. So there's a variation in y which has been explained by x, that is ESS. Then there is variation which in y which is not explained by x, which remains to be explained, is the RSS. And how much variation was there to be explained in y is the TSS.
Sir, the difference between the T test and the F test you told is that the F test is combined test for all slopes and T is for one slope only, right?
Exactly.
Okay, sir. Thank you.
The t-test is performed as many times as there are slopes in the regression. So if there are 5 slopes in the regression, if there are 5 x's, there will be 5 slopes. So you will undertake a t-test 5 times for each of the x's. So whether a particular x affects y is understood by testing that x's slope using a t-test and its p-value. So we come to know that a particular x affects y or not. If you are able to reject the null hypothesis for that x, you will say that that x affects y. And there may be another x in the same regression which has a p-value greater than 0.05, which in which t-test, if you perform, the null will not be rejected. So you would say that x does not affect y. So it can happen that some x's affect y and some do not in a given regression. So you can know it by doing individual t-tests. And if you want to run a single test that would tell us about the entire regression and all slopes in one go, that would be a F test. So F test is just another test that we can do to verify what we are trying to see. Now coming back to the Excel sheet, there is 1 or 2 points that I want to explain. I'll take 5 minutes to explain that. What is your finding here? You can see the p-value of beta 1 is more than 0.05. So your result is do not reject the null. The p-value of beta 2 hat is also greater than 0.05. So again, your result is do not reject the null, right? Because p-value is 0.49, which is greater than 0.05. So you are not able to reject the null for beta 2. That means in this case, x does not affect y, right? So this slope coefficient, which is minus 0.5, will not be interpreted in this case. So you will not say that if x rises by 1 unit, y falls by zero point 0.5 units. You will not say this because you have to check the p-value. If it is greater than 0.05, you are not able to reject the null that beta 2 is 0. That means beta 2 is actually 0. So when beta 2 is 0, it's not 0.05, which is in your sample. Actually, beta 2 in the population is 0. So in that case, the population from which this sample was collected, there was no relationship between x and y. So we conclude that there is no relationship between x and y, and x does not affect y in this case. Now we are able to say something about population using our sample. So that's the beauty of hypothesis testing, the whole exercise that we just did. So I'll upload this PPT, oh sorry, this Excel file also today. It's a little bit messy, but because you were there in the class, you understood where I have written what. To somebody who is looking at it for the first time, may not be able to understand anything from here. But because you were present in the class, so you know. Uh, if you have any question now, you can ask. I'm closing the class. We will meet next time and continue from here. You can keep your questions for future also. So you can refer to the videos and then you can ask further questions later. So it's not that you have to ask a question now only. Of course, this PowerPoint that I have just written with my pen, I'll be uploading this also. It's not from the Gujarati book. I have written it from my pen, so I'll upload this also for your reference. All right, so who is absent? Priyank, please send me the list of absentees.
Yes, sir, I'll do that. Also, sir, since we have covered a lot many things in a short duration of time, not exactly a short duration, but yeah, a lot many things which are new for us.